In this class, we're going to take a look at the limit of a sequence. So a sequence can either converge to some limit or it diverges and doesn't go to a limit. So if you've got a sequence, so let me just say sequence, then the behaviors are that that's either going to converge, and if it converges towards some limit, which is just some number that the terms in the sequence are getting closer to, although the terms in the sequence will never actually reach that number. They'll never get to the limit. Can't get to the limit because the limit is just like an aspiration. It's not one of the numbers of the sequence. So that's what happens when it converges. Conversely, if it diverges, then it doesn't have a limit. So diverge. If it diverges, then it might shoot off to positive infinity, so the numbers are just getting bigger and bigger and bigger every time. It could shoot off to negative infinity, where they're just getting smaller in an unbounded way, so they keep on getting smaller. Or it could just be that the limit does not exist for various reasons. So one common reason why the limit does not exist is that you've got a sequence which alternates. So if it alternates and it goes positive, negative, terms in the sequence, then by definition that does not converge to a single limit. So we say that that one does not have a limit because it alternates. So that's basically what we're looking at, but we want to focus on this, in this class, on the scenario where we do have a limit. Or at least start to think about a little bit more about what it means to have a limit. So I've got some examples and we're going to run through them and see what happens in these examples and what we learn about limits, convergence, divergence, and pulling that all together. So the first one here is 1 over n. So these are just the rules, by the way, to generate the sequence of numbers. So we'll maybe just for each of them start to write out some of the numbers. So for this sequence here, we would start plugging in from n equals 1. So we're just going to plug in n equals 1, n equals 2, 3, 4, etc. just until we get enough of a feel for how the sequence is working. So 1 over 1 is just 1. And then 1 over 2, obviously 1/2. And then you get 1 over 3. And then you've got 1 over 4. And that is just going to continue on indefinitely. So as you go further and further down the sequence, you're getting closer and closer and closer to 0. So 0.5, 0.3333, 0.25, you're just going to get closer and closer and closer to 0. You're never going to get to 0. You can't get to 0. There's nothing you can divide 1 by to give you 0, but you can get as close to 0 as you want by choosing an n value as big as you want. So eventually, in fact, fairly quickly in this sequence, you're going to end up getting pretty close to 0. So we say that that guy tends towards 0. So that one does have a limit. So that one converges to 0. And 0 is the limit in that case. So let's have a look at this guy here. So just again, plugging in the different placeholder values for n. So n is 1, 2, 3, 4, etc. So this time it's similar to this one, 1 over n, but we've got a 1 in front. So it's 1 plus 1 over n. So here we're going to get 1 plus 1 over 1. So 1 plus 1 over 1 is 1 plus 1, which is 2. So the first term in that sequence is 2. And then we've got 1 plus 1 over 2, which is 1 plus 1/2, which is basically just 1.5. And then you've got 1 and 1/3 to write these as mixed numbers. And then you've got 1 and 1/4, etc. So if you look at these numbers, the fractional part, they're getting closer and closer to 0, like this guy up here, but the 1 is never going to disappear. The 1 is going to stay there. It's only those guys that are changing. So you're always going to have 1, each number will have 1 plus a number which is getting closer and closer to 0. If you go far enough down that sequence, then you would end up with this part being insignificant because it's so close to 0. So eventually, this guy would just tend towards 1. Okay, so that one is also convergent. A convergent sequence, it's converging in, it's getting closer and closer to a limit of 1. So I wanted to put that example in just to show that not all sequences which are convergent converge to 0. A lot of them do, and there's particular types of sequence that will always kind of converge to 0, but they don't always converge to 0. I mean, that's a very simple example. You could put any number in there and start to modify this in some way and make it convergent to some number. So it's easy to think that they either diverge by going to infinity or minus infinity, or they converge to 0, but there are more nuanced cases in there as well. So let's take a look at the third one. So x sub n equals 2n. So just again plugging in the numbers, or maybe just write this one over here. So putting in n as 1, 2, 3, just n is a placeholder number, so that would give us 2. So 2 times 1 is 2, 2 times 2 is obviously 4, 2 times 3 is 6, 2 times 4 is 8. So this guy is going up in 2 every time because we're multiplying the n number by 2. So that's just going to carry on in an unbounded fashion. It's not growing very quickly. You're only adding 2 every time, but it's not approaching any limit. It's getting bigger and bigger and bigger. You're always adding more numbers. So this one is actually just going to shoot off to positive infinity. So just as a reminder, we do get sequences which have no limit. And this one is said to diverge. So diverges to positive infinity. Okay, so example number 1, 2, 3, 4. This guy is minus 1 to the power of n. Fairly common structure, that actually, a negative number with some power on it. So just again putting in the values for n. So we'll start with n as 1. So if n was 1, we would have minus 1, because that's minus 1 to the power of 1, which is minus 1. Then we've got minus 1 squared, but minus 1 squared is minus 1 times minus 1, which is positive 1. So that goes to 1. Then we've got minus 1 cubed, which is minus 1 times minus 1 times minus 1, which takes you back to negative 1. Effectively, what we're doing here is just multiplying by negative 1 every time. So that means that when you land on a negative and you multiply that by minus 1, you go back to a positive 1. And if you land on a positive and multiply that by minus 1, you go back to a negative. So this is an example of an alternating series, a sequence, sorry, not a series, alternating. And an alternating sequence, by definition, cannot converge to any limit. So it doesn't have a limit. So we would just say for this one, the limit does not exist. But it's slightly different to this guy up here. It's not diverging to positive or negative infinity, because it's alternating. By definition, it doesn't exist. The limit doesn't exist. Okay, so they're fairly common examples actually. You'll see variations on them. So you'll see quite a lot like this, but it might not always be minus 1. It could be a minus 3 in there, or some other number. It could be something slightly different here. The same over here. This could have been a 2n or an n squared, or different variations, but similar kind of behavior. So looking at the last one obviously looks a lot more complicated. This is kind of the direction you might be going in with these types of questions. So does this one have a limit, or does it not have a limit? So we could start generating terms to see what happens, and that's fine. It's always good to be able to look at the terms and base your feel for how it works off of the terms, but there is an algebraic approach to this as well, and this is possibly a little beyond the scope of this class, but I'm just going to show how we would go about tackling this guy. So one thing we could do is to start generating the terms, but it's going to be a little cumbersome. When we start putting numbers in here, 1, 2 are okay, 3 is kind of okay, starts to get a little bit bigger numbers after that. So let's think about how we can maybe do this slightly differently. So what we do in a scenario like this is we try to simplify or rewrite the expression that we're given in a slightly more useful form, because looking at that form there, it's not obvious whether that converges or diverges unless you've got a lot of experience with this type of setup. Looking at this guy here, it's kind of obvious that that one's going to converge to 0, because making the n bigger is going to make the overall fraction smaller. But it's not obvious here at all. Who knows, like, just by looking at that, what's going to happen. But one thing I will point out is that these n squared terms are much bigger than the other terms in the numerator or the denominator. They dominate. I mean, the only other term here is a 1, and you're actually multiplying the n squared by 3 to make it even bigger again. So this term really dominates the denominator, and that term dominates the numerator, and that's going to kind of pop out later in the sort of algebra. So what we can do here is, if we look for the highest power, which is n squared, and divide top and bottom by n squared. So we're going to divide here by n squared, and we're going to divide here by n squared. So just writing an equivalent fraction, because we're not changing the fraction by doing that, we're just dividing top and bottom by the same thing, which is fine. You're allowed to do that. So if we divide each term by n squared divided by n squared is 1. 2n divided by n squared is 2 over n. N divided by n squared is 4 over n squared. Okay, so still with me? 3n squared divided by n is 3, and then 1 divided by n squared is 1 over n squared. So you might think, why is that useful? That is ugly, I don't like this, make it go away. Well, it's useful because of another concept, which again might be beyond the scope of this class, but when we're evaluating a limit, we actually use certain notation for that. So we say lim for limit, and we want to consider the limit of a certain behavior. And what is the behavior we've been considering? Well, we've been considering the behavior as n approaches infinity. Like, we're thinking what happens when this n number gets really, really big. In other words, you go way, 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 way down the sequence, tending towards infinity. So we're not talking about the numbers in the sequence here, we're talking about the placeholder number. So as you go way, 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 way down the sequence, what happens? So we write that by saying that the limit as n tends to infinity. And that's just a way of saying what happens to the sequence, does it have a limit as n gets bigger and bigger and bigger? So we can pull that in over here and actually write that in front and say the limit as n tends to infinity, and then consider what happens there, because that's what we want to know. We want to know what happens to this guy, which is just a rewrite of this guy as n tends to infinity, as n gets really, really big. Well, if n gets really, really big, then that guy there is going to get really small, because we're dividing by n. We're dividing by this huge number. 2 divided by a huge number is basically going to be 0. 4 divided by a huge number squared is definitely going to be effectively 0. It's going to be so close to 0. This term here is also effectively going to be 0 because it's going to be so close to 0. So when we take this limit, then all we're going to be left with is the 1 and the 3. The 1 and the 3 do not have an n in them, so that means that they can't be affected by n approaching infinity. So we end up with just 1 over 3. So it turns out that 1 over 3 is the limit. 1/3 is the limit of that sequence, which is kind of surprising, and just by looking at it, there's no way to think that that might be the limit. If you started churning out the terms, they would slowly, slowly, slowly approach 1 over 3. That's where they would end up going in that direction. The reason why that's basically happened is if you look at the original expression, like I mentioned earlier, these two guys here are dominating the fraction, and this here is 1n squared, this here is 3n squared, which effectively means that you can forget about these. They're almost playing no part in the sequence because those terms are so much more powerful. If you're ending up with just those guys there and you divide top and bottom by n squared, you end up with 1 over 3. So kind of loosely thinking about it that way, that's why 1 over 3 ends up being your limit, because of these dominant terms. So just a quick recap of what we've talked about there. We've been exploring the idea of a limit of a sequence, and the limit is just the number that the sequence terms approach as you go way, way, way down the sequence. So this guy here approached 0, so it had a limit of 0. The guy that I had here previously approached a limit of 1. This guy didn't have a limit, so it said to diverge. This converged, the other one converged. This was an alternating sequence, so it does not have a limit by definition. And then this more complicated example, we pulled in the idea of evaluating a limit like this. We did this kind of little algebraic trick, which, it's just a thing. You would need to just know how to do that. That then exposed the fact that these terms really dominate the expression, and when you take the limit, everything else disappears and you get 1/3. So quite surprising that, looking at that, there'd be no way to really know without experience that that would approach 1/3. So it's a more complicated example. But get a bit of experience if you can working with these kind of more intuitive examples because they are still going to be very important as you explore sequences further. And when you get to a certain point with those, you'll be able to start to take on these more complicated expressions once you've got the experience with these guys here. So that's basically how we consider the limit of a sequence.